Okay, now we are recording. So yes. Side channels. We have information we want to communicate. We primarily do it through the main channel. However, there is also secondary information related to this information we want to get. And so this is a side channel, the means through which we obtain secondary information. This doesn't contain the actual data we want. It contains other stuff that's somewhat related, but not really. We have to do a bit of guesstimating using probability and hey, how correlated are these two things to figure out what we actually want. And the most prominent example, I would say, is Among Us. I'm assuming everyone here has some idea of what Among Us is. Okay, cool. Okay, good. Because last time I tried to explain this, they had the person I was talking to had no idea what Among Us was. So it was interesting. But anyways, in the game of Among Us, we have some information we want to obtain. For example, who is imposter? Main channel for communication would be if we see them kill someone, they're clearly imposter. But oftentimes that's not how we discover them. We discover it through side channels. Maybe they're acting a little sus. Their speech is varied. They're not really acting how they normally would. That's the idea of a side channel. And we can guess, hey, they're acting a little sus, so they're probably imposter. And that's true, not just for games, but for everything in general. Computers also are sus. They have side channels that we can exploit, and there are a lot of them. So I want you guys to put on your thinking cap, that let's think about what possible things could a computer do that reveals some information. Does anyone have any ideas of some aspect of a computer that might reveal information? Yes, you. Time zone? Yes, time is a very important aspect to side channels. It's probably one of the most prominent introductory examples for a side channel is the time attack. Basically, different computations are going to take different times. Let's do a very simple example of just a password checker. So you can see here, we have a password checker where it's very standard implementation. We just go through character by character and compare. Hey, does it match? If not, then we're going to return. This seems like a reasonable way to compare passwords, right? But there's one big issue. We return. So this is actually going to make it so for different passwords, as you can see here, our first one where everything matches, we go through all the loops. But if you enter something that doesn't match, for example, that 7564, it terminates immediately. That's going to be a difference in time. The first one, we go through 4 characters. That's a lot of time. The third one, we don't even get past the first one. So it's going to end very quickly. So in other words, we can figure out a password by just timing how long does it take to check the password. And you can actually see here, I included a graph of a pin tracker where we're testing what the first character in our pin is. As you can see, one of them takes a bit longer than usual. So does anyone want to guess what the first letter or the first number in our pin is based on this graph? Any clues? Which number looks out of place or looks different from the rest? Yeah? It is going to be 4. 5, you look, it's kind of close, but you see it drops down once we hit 5. But yeah, the first character is 4. So this actually makes brute force and passwords a lot quicker than usual, because usually we'll have to guess all possible combinations for pins. In this case, you can just go number by number. So for a 4-digit pin, that's just 10 guesses for each digit, so 40 in total. While normally it would be 10 times 10 times 10, so 10,000. So this is the idea of the time and the time. Different inputs are handled differently, which results in a difference in our side channel. In this case, time is our side channel. There's a difference in time. So that's not good. We want to fix it. Does anyone have ideas on how we could fix this password checker to be foolproof to time and attacks? Yes, you. Yes. Go through the whole thing. That's a great idea. And that's actually what we're going to do. Let's go through the whole thing now, because the problem was we told me earlier. Oh, actually, yeah, here you can see another thing of really compare. But here, let's go through the whole thing. And as you can see, I took an image. You see, oh wow, they look very similar now, right? You can barely tell the difference. But if we zoom in, you still see a difference. Huh, that's really weird. I wonder why it's doing that. Clearly, there's been an improvement. Your idea was great. It drastically reduced the difference, but there's still a difference. If an attacker is dedicated enough, they can figure it out. Yes, you. Brilliant. Yes, that's exactly what's going on here. We are now going through the whole thing, but there's still a difference in execution. We have an if statement. Inside this if statement, we assign something. That's an operation that's going to take time. Outside of the if statement, there's no operation, doesn't take any time. So if an input has more characters correct, it's going to take longer. And we can still pick up the channel, pick up the key through our time and attack. So that's no good. What are we going to do about this? How are we going to fix it? Any idea? Yes, you.
Jump operation.
Jump operation. Jump operations. Oh, like a dummy variable that we just do something to. That's a great idea. That's exactly what we're going to do now. Surely that's going to fix it because now you see, hey, if else looks exactly the same. There's no difference in code execution. And you can see, wow, that looks basically the same. But let's zoom in again. And this time we're going to have to zoom in a lot because it's very similar. And we see, oh, just barely. There's that difference there. It's so weird. Why do we still have a difference? They look, oh, yeah, you know?
Because in CPUs, when you compare in that branch, sometimes it might take 2 cycles if you fail a branch or not. It's like more knowledge.
Can you explain that again? I don't think I'm fully processing.
So like when you do a comparison and then you have a conditional branch,
yes,
it could take multiple cycles to take the branch rather than failing the branch and falling through.
Ooh, that's interesting. And yes, you would be correct in this case. That's why there's still a tiny difference. Even though the surface high-level code looks exactly the same, computers are very complex, and they have a bunch of micro-architecture things going on to optimize it and do things quicker, which you will learn if you take computer organization. So this doesn't work either because of, well, caching to some extent, but also, like you said, the instructions take a different amount of cycle for each. Good point. That's really good. So, oh, Adam, you have something to say?
What does caching really mean?
Caching here means, basically, I think part of it is branch prediction, but part of it is also caching because you see how we have the assign variable. So like assume we have dummy variable in cache, but not the good variable. And if we have dummy variable go many times, then it's cached. It's going to be quicker to fetch each time when it's consecutive like dummies.
Okay.
But if we have some good in there, then like we have to get it from main memory. So that takes slightly longer.
What is it?
It's like, I have a different example later on if where caching really shows up in a time and attack. But yeah, for this one, actually, I think you're right. Branch prediction is probably what does it well. But yeah, anyways, we still have a problem here. We need to fix it if we want secure code. So how are we going to fix something when it already looks like it's exactly the same? We need to develop code that does the same exact thing no matter what our input is. Yes, James.
To do it and or.
And or, yes. The key to this is math. If we just do an XOR operator, then it's the same exact thing no matter what. You see, there's no if statement. we do the same thing. So what XOR does, it's basically a math operation that compares two bits. And if they're the same, it results in 0. So in this case, if everything is the same, we're going to get 0 each time. And so when we add it all together, in the end, we have 0. And no matter what we put in, we still do the maths. We get the same thing in the end. And you can see in the timing diagram I have right there, it looks basically the same. It's very hard to tell the difference. Yes, Adam?
Doesn't it take longer to add a non-zero value than a zero value?
No, it doesn't, because they have a set number of bits, right?
I don't know. I mean, that's
Wait, why would it take longer?
It's the same thing.
It's the same time.
It's the same thing.
Because like don't you have this other bits here, set of bits here, and you just go pairwise to add?
I don't know.
I'm not entirely sure.
I guess.
I mean, if you doubt it, you can run it yourself. I prepared an example and posted it in the Discord. So after this GBM, you can go through and see all of the things yourself. But it does get really interesting when you get in deep into it. Okay. So yeah, that's that. That was a time and attack, but let's look at a time and attack in a different scenario. This one is going to start talking about cache. Yes, you have a question. Go back. Got it. Yes. What do you want to say?
A size. Like if there wasn't this would be that size.
If they forgot the size, yes, you would have.
If size is like size.
Yes, that's a great point. So here, you found another example of a time and attack, because there's one where we're checking the numbers, but also if size is different, we return prematurely. You're completely correct. This is bad code because it allows attacker to figure out what the size of our password is just by going through it. So in that case, how would you fix this? Do you have any ideas? Or does anyone have any ideas how we would fix it? Yeah?
I'm just curious, could you just basically tell it to always take the same amount of time? Like you could take the difference of time it's going to take and then just add more time.
You tell the program to always take the same amount of time.
Well, like you just, like for instance, if it takes more time than it should, you just tell it to, wait so many nanoseconds. Like, is that a thing you would do?
That is a thing you can do. There are certain operations that allow you to wait a specific amount of time. The difficult question is, how do you measure how long it takes?
Well, like you just have a time operation at the beginning and the end, and then if it doesn't take as much time as it should,
then you just
like
wait and
yeah, like it's O time. If it doesn't take the amount of time
Yes.
it should take, you just add more.
yes, that's a valid way of
You
doing
also
it.
have to like take
Yeah.
into account like if you're running it on a super slow machine, if it might reach that deadline.
Yeah.
So it's like unreliable.
But yeah, that's the point. Like on the machine, the harder you run, that's going to affect how quickly it runs operations. But yes, what you said is a method that they often employ to deter time attacks. They would just have time buffers to wait until some amount of time passes. I guess the main problem with that is now your code is slow. But right, that's the problem. That's what we are willing to sacrifice for the sake of security. Yes, James?
So Adam's point about adding zero being shorter, I don't think it is. You could also just replace add with or.
Add with or works the same. Oh, it's brilliant. Yeah, actually, that's a way better. You're just getting on board.
Tested some of the XOR, you just do and or.
And or.
Get the XOR stuff like it's like.
That's a lot smarter. Yeah, I like that. So if you wanted to implement super duper secure code, do what James said and do and then or.
Yeah, that's the.
You're wrong with this code.
Okay. Okay, then. So I'll move on to caching. So I guess I'll explain briefly what caching is. I'm assuming most of you have taken computer organization. No? Okay, I'll just explain it. So basically, in a computer, we have memory where we store the variables that we use, but not all memory is created equal. Specifically, we have different like tiers of memory organized in a hierarchy. This is known as caching. So we see at the very top, we have our registers. Registers are the closest to the CPU that's actually doing the operations. And so it's going to be really, really quick to access our registers. You can see it takes only one cycle. The problem is that these super fast registers are very expensive to make. And so we can't have a lot of it because it's so expensive. So as we go down our hierarchy, it becomes slower. But since it's cheaper, we can have more memory. So typically you'll have your cache, it's very small, can only hold a few variables of data, but it's pretty quick. And so the reason I bring this up is this creates a difference in time. If something's in our register, we access it very quickly. However, if something is in our cache, we also access it quickly. But if it's not in any of our caches, we're going to have to get it from main memory, or worst case scenario, the hard disk itself, which is going to take so long. In fact, in a lot of algorithms, the main thing that's slowing down our computations is memory access time. So yeah, but there's one nuance I want to explain over here. We don't just have one cache, we have several tiers of cache. You see L1 cache, L2 cache, and L3 cache. What does this mean? Why do we have multiple sets? Well, it's because we want our hierarchy, because we can't have a lot of L1. So let's just split up into different layers to try and make it quicker. How it works is if L1, for example, wanted to access a piece of data, such as this cookie, it's going to check in its register. Does it have it? No. It goes to L1. Does it have it? No. L2? No. Goes to L3 cache? No. So it's going to load that bit of information from the main memory, and it's going to go all the way up. And so now it's in all of our caches. If we ever want to access that data again, it's in our cache, we can get it really quickly. Similarly, if we are done with a piece of data and we want to remove it, it's going to cascade down and go all the way and remove it from each of the caches. I will note this is a specific type of caching known as inclusive caching. Because if something is included in the L3, it's included in everything before. There are other types of caching, such as exclusive or non-inclusive, but those are harder to implement. And they suffer from similar vulnerabilities that we'll get into. So for caching, does everyone follow? Okay, yeah. Basically what you need to know, hash is quick. So why is that important? Because we can attack that using a flush and reload attack. The idea is we're going to flush our cache, completely empty it, so there's nothing in it. If it's empty, then when a different user tries to access data, they're going to put it in their cache. So if we try to access that data again, it's going to be really quick because it's in cache. However, if our other user never accessed that data, then when we try to access it, it's not in our cache. It's going to be super slow. That creates a difference in time. So far, does anyone have questions about this? No? No questions or concerns about how it's implemented? Okay. One thing I want to point out is when I first learned this, I thought it was kind of weird that a different user can access my cache. Because right now we are talking about two separate processes running, the victim and the attacker. And that's why I bring up this idea of we have different layers. Because the L3 cache is shared among all the cores, among all the processes. So if anyone accesses that piece of data, it's going to be in the L3 cache, right? So if I'm core 0 and I try to access that data, it's in my L3 cache. That's why it's quick, right? Because we all share that L3. So I just wanted to point that out in case anyone was a bit sus of that. But anyways, that's the flush part. We remove our cache, and the reload is when we try to access that data again. And so you can see here on the first hand, it's very quick because our victim accessed that piece of data. On the other hand, it's very slow because our person didn't access it. And yeah, that's essentially how this works. Cool. Now let's go into some examples of how this is actually done. Actually, solutions we'll skip for now. No. Let's talk about solutions. Okay. Does anyone have ideas on how we can fix this? Because obviously this is bad. We don't want timing differences because then people can pick up our secrets our data is our cryptographic keys. Oh no. So how do we fix the cache? Oh, how do we fix this problem?
Don't share the L3 cache.
Don't share the L3 cache. Great idea. Yeah, obviously not sharing the cache is like duh, the obvious answer. There's a slight problem with that. Even though our cache isn't shared, if we don't have like shared functions that we can call, there's a thing called mmap, memory mapping. So if we have that executable, the binary, we can kind of force a shared memory by just mapping it. And then we can access the same memory that that process is accessing. But yeah, that's a great attempt for a solution, but unfortunately, it doesn't work. Any other thoughts? Yes, Adam?
Try flushing it yourself after every memory line.
You want the user to flush after they access the data.
Process.
Oh yeah, the process. That would work. Assuming you do it quick enough, it would work. And yes, that's a great idea. Flushing takes a while though. Processes aren't going to do that because that's going to slow them down so much. But if you actually want it to be secure, yes, flushing instantly after would work. Nice. James?
Just don't use the cache.
Don't use a cache. Even that's an idea. You can build a computer that has no cache at all. Sell it on the market, see how it goes.
Wait,
Okay. Anyone else want to say something? No? Okay.
yeah, wait, sorry.
Okay, yeah, then.
What's the attack like surface or like scenario here that's two like the victim and attacker on the same machine,
Okay.
not on the same process?
They would be on the same machine, but in different processes.
Okay, yeah.
That's how it would work.
Okay.
Yeah. Okay. Yeah. So here's some other thoughts. The flush instruction, because that's how we were able to detect the difference because we flushed it from cache. What if we just got rid of the flush instruction entirely? Then we can never remove things from cache, and it would be great because we can't detect the difference. The problem with that is we don't need a built-in flush instruction to empty the cache. There's this idea where if the cache is full and we try to access something new, we need to put it in the cache, but it's already full. So how are we going to do that? By removing stuff already in the cache. So instead of flushing, we will just access a bunch of dummy data so that the cache is completely replaced with our dummy data. Okay? And this is known as the evict and reload attack because we are evicting all of our data from cache. Another solution is just don't have any timer, like any timer function on our device. One super high precision timer is RDSTC or TSC. You'll often see it used in time attacks. So what if we just got rid of those timing processes? Then we can't measure how long the attacks take, right? Does anyone see something wrong with this approach of just getting rid of the timing function? Adam?
How on earth is a computer gonna work?
That's true.
How like clock cycle?
Oh, well, you could still have a clock cycle, but just have no way of accessing the clock cycle.
RTSC counts instruction cycles.
Yes.
It doesn't count time.
Yes. So what if we just got rid of RDTSC completely? Is there a problem with that?
Oh,
That's what I'm suggesting. Get rid of those instructions that count the cycle time or the cycles that run.
so like modify the CPU.
Modify the CPU so that it can no longer count the number of cycles. That's what we should do for all future processes. It can't count how many cycles were done.
Sounds good to know.
Sounds good to you. Okay. Anyone have any objections to this solution?
Can you not just add in a loop and you have effectively the same thing?
Exactly, James. If you don't have a timer given to you, you can make your own timer. I can count 1, 2, 3. That's a timer. I can just create a function that loops and increments over and over to do the same thing, to act as a timer. So even if we don't have a built-in function, we can just count in a thread, as it says on the slide. Shared memory we talked about, and then what about reload? Actually, yeah. What if we're not able to reload our data? For example, the premise of this attack is that the user accesses data, our victim accesses data, and so then we access that same data. What if we just prevented the attacker from accessing that data? What would we do then?
How would you do that?
So in this context, it would be that the data we're looking for is a specific function. Like if they call this function, then we know that their key had a 1. Like if it's a 1, we call this function. If it's a 0 in this bit, we don't call this function. What if we just made that function exclusive to the victim process and prevent any outside users from calling that function? That's the idea there. Are you following? Or do you not?
When you say function. What do you mean?
Here's an example of a function. Square number. Okay.
No, not function.
Not following? Okay. We'll come back to it later when we talk about cryptography, see if you follow them, okay? So we'll start about cryptography. Yeah. So basically the main place where we're going to see timing attacks is cryptography, because we love getting people's secret keys. And cryptography is just a bunch of math, as you can see here. I will not go into the math, I will just generally explain it. How RSA works is it takes advantage of the fact that multiplying numbers is easy, but factoring numbers is hard. Because of math magic, we can do this thing where if we have modulo of a number, so modulo basically means like 5 mod 3, that's 5 is 3 plus 2, so it's 2 mod 3. Basically, we just truncate our number, is the idea of modulo. So the whole thing behind RSA cryptography is we're going to take our plain text, the message we want to communicate, and multiply it by our encryption, as you can see there. And the idea is it's easy to reverse that effect when we know the factors, but if we don't, it's going to be super difficult. And so how it's going to work is I have a secret I want to share with you. I know what my factors are, so I can easily undo the effects. And I'm going to tell you, hey, if you want to send me a secret message, you're going to multiply by this huge number and do math with this huge number. And then you send your result back to me. Since only I know what those two factors are, I can undo your multiplication. I can undo the math you did. If anyone else intercepts our message, all they know is that super huge number they can't factor. So they can't figure out what the plain text actually was. This is the idea of a trapdoor function, a function that's easy to do one way and difficult to do the other way. This is the basis of RSA encryption. To make it more efficient, so you see, let's look right here. Yeah, and the encryption step and the decryption step. You see how we raise a number to a power? That's basically the bulk of what's taken time. We're raising a number to a really big power, and we have to calculate that. To make it more efficient, we can do something called fast exponentiation. The idea is, hey, let's say we were raising a number to the power of 37. One way we could do that, for example, like what's 8 to the 37th power? We could do 8 times 8 times 8 times 8 times 8 times 8 times 8. Do that 37 times, but that's slow. Instead, what we can do is we can split up into powers of 2. Because we could do 8 times 8 is 8 squared. And then we can just square 8 squared to get 8 to the 4th. So the idea here is if we represent our number in binary, you see there's going to be 1s and 0s. So each time, we're going to square our number. But if there's a 1, we need to also multiply by a number. For example, I guess that first digit, the 1, that's saying, hey, we need to multiply by our number initially, and then we can square it. Are people following? Okay. Yeah, it seems like people are generally following. So this is how the cryptography works. The question is, how do we exploit this? Well, you see there are two different functions, the square function and the multiply function. These are going to be two separate functions in our victim's memory. So if we can flush the cache, then every time they need to call these functions, they need to load it back into their cache. And then we can just call the square function and see how long it takes to access that. So that's actually what I have here. This is some time and data from when we ran an attack against a user. You can see that there's the square function represented by red and the multiply function represented by green. And you can see, hey, sometimes the square function was really quick, sometimes it's not. And instead, the multiply function is really quick, as you can see with that M over there. And this is possible because our function is either in the cache, but it's not, and that's going to take different time. Any questions on this? No? Anyone want to propose a mitigation to this? No? Yeah, that's fine. The idea is if we wanted to make this secure, we would just not have two separate functions that we only call some of the time. There's an implementation known as square and always multiply, where it's just every time we multiply by a different number. And because we don't use different functions, we can't pick up the secrets. But that's RSA. And then next, I have another encryption algorithm. Yay, we love cryptography. This one is AES. So like the two main crypto algorithms you'll learn about are RSA and AES. These are the big boys. RSA is basically just math. AES it does weird blocky table stuff. So how AES works is we're going to organize our data into a nice little table like that. And then we're going to do a bunch of things. First, we're going to substitute each of our numbers for a different number using something known as a lookup table. Basically, if we see this number, the table tells us what number to replace it with. And then after that, we're going to randomize all of our data by shifting the rows and then mixing the columns. And finally, we're going to use our key to XOR the data to get our final thing. This is one round of the encryption. And we're going to repeat this at least 10 times. So AES is essentially an idea of let's just mix all of our data and XOR it a bunch of times. And it's so confusing that I don't even understand it. So the attackers probably can't reverse engineer this and figure out what the key was. And I mean, like looking at this, it looks pretty complicated. Yeah. In fact, it's so complicated that I don't even know how to implement this. Like in a processor, how are we going to have AES doing stuff? Yeah, Adam?
Fun fact, the
Yes.
Intel architecture has assembly for AES.
It has assembly for AES, as in like a specific function just to execute AES.
Basically.
Yes, exactly. That's one way you can do it. You can have in your processor a pre-built instruction saying, hey, this is how you do AES. And that's what this is right here, ASNI. It's basically saying, these processors, we're going to build in an instruction to do AES because it's complicated and it's super important. That's one thing you can do. And Intel does do that. But what if you have a different device that doesn't implement AES-NI because they just don't want to? There are devices that exist that do that. In this scenario, they're going to have to do something different. Instead, they have to do a T-table lookup. Basically, they have a big table saying, okay, if this is my input, after all of the random stuff that happens, this is what my output is going to be. So you just look up in your table saying, okay, I input this. Oh, this is what I'm going to get out. Okay, cool. And then our encryption is just a bunch of lookups. When we do that over and over again. Yeah. So that's the cryptography stuff. Now let's think about how can we exploit it? Because we are attackers using side channels. We just learned about tenant attacks. I wonder, what's being cached here? Yes, you.
People fix the lookups for different things. Those both parts of that would have.
Yes,
The parts that had to actually go on that.
exactly. That's exactly correct. Nice job. basically, every time we do a lookup in our T table, we have to cache it. At least every time the victim looks up in the T table, they have to cache that part of the T table. So now it's in cache. And if we just iterate through all the entries in the T table, we can figure out, hey, what's been cached? And then we can figure out what their key was, because the key determines which parts of the lookup table we access. So in other words, we can figure out the key that they use to encrypt AES, which is, because now we can break AES. We've broken RSA and now we can break AES. I want to mention a slight nuance. The cache is bigger than individual entries in our T table. As you can see here, our cache is 64 bytes, but each entry in the T table is only 4 bytes. So we actually have multiple entries in the cache. So that leads to a problem because now we have multiple things cached. We're going to get multiple false positives. How do we deal with that? And the main approach is let's just run our bin a bunch of times. If we run it a lot of times, then sure, we get like multiple false positives. But if we run it like 100 times, only the correct one is going to be a positive every single time. And that's how we would break this. So you'll see a recurrent trend that how do we make things harder for attackers? We fix some stuff, make it more difficult. What do the attackers do in response? Let's just gather more data, like a billion times, and then we'll figure it out. That's kind of a trend in side channels. And yeah, last bit, time and probe. So this is basically the idea of what if we can't access that function. Because going back to RSA, we had those two functions we wanted to access. What if we just couldn't access them? What would we do then? We're going to prime and probe. This is sort of like flush and reload, except we kind of flip the concept on its head. Before, we were checking if the victim's data has been put into the cache. In prime and probe, we're instead going to see if the attacker's data, is in the cache. Basically, what we're going to do, we're going to prime our cache by putting in our data. And then if the user accesses some piece of data, then they have to replace something that we put in cache. Because if the cache is full, we can't add more stuff to it. So we need to replace what we put. And so after we wait for a bit, we're going to probe the cache again and see, hey, is that data we put in there still there? That's the idea of prime and probe. And how you implement this is going to depend on how the cache replaces data when it's full. There's different policies you can learn about. First in, first out. So like the very first piece of data we put in is the first to come out. So when we're probing, again, we would just check, hey, what was the first thing we put in? If it's no longer there, then we know, hey, they accessed that function we were interested in because it replaced what we had. There's last in, first out. So basically now instead of checking the first thing we put in, we would check in the last thing we put in. And then least recently used. So that's prime and probe. That's all of my time and attack grants. This presentation is mainly about time and attacks because they are the easiest to get into and they are very well explored. Are there any questions on what we've covered so far? Yes, yeah.
So with like a FIFO, LIFO, and LRU, could you have theoretically like a piece of hardware where like some of its caches are FIFO, some are LIFO, some are LRU? You like mix it up so that like an attacker wouldn't really know what to expect.
That's an interesting idea.
Like, has anyone ever?
I don't know if anyone's done that. I don't do that.
I don't know if anyone's done that, but all of those things are characteristics of the hardware itself, which usually is you can reverse engineer or you can just look it up. Like if you look at the cache in your like phone, you can figure out what kind of cache it's using and what kind of caching algorithm or replacement algorithm.
So even if they try to implement some kind of way to obfuscate it, attackers just could reverse engineer.
Yeah.
Do it themselves.
Very long, it's not a chip.
Okay. Anything else? No? Okay. Then I'm going to be done with time and attacks. Anything else? Any other piece of data we could look at? Right? Yeah.
Just broadly speaking, the electrical signals.
The electrical signals. Do you mean like electromagnetic radiation?
Radiation, yeah.
Okay, okay. Yeah.
Also, yeah, voltage.
Voltage. Okay, yeah, you actually just picked up two different side channels we can explore. Electromagnetic radiation emitted by our device, and also the voltage or power consumed by our device. So let's look at electromagnetic first. I don't have a lot of stuff here because it's not super interesting, but yeah, basically. For like all of these, I have like real life examples of like, explain that. When I was looking at like EM side panels, they're just like, I don't know. I don't know, man. Sorry, I don't know. I read once that in like 1960, there was spies spying on like the NSA, I think, by just having a radio antenna in a nearby building, just looking. Yeah. I don't know.
Can I hear
Yeah,
it?
yeah, go ahead, go ahead.
I think this is relevant. I know people who implant magnets into their hands because electricity, when it passes by a magnet, creates electromagnetic forces. So there are some people who implant magnets into their hands or their skin or something because when they pass by electricity in a wire or something like that, they can feel the force on their magnet and they can determine that there's electricity running somewhere.
Yeah, I'll get you.
There's not useful, except you can feel like electricity. It's a side channel.
It is a side channel. It's pretty cool. But it's for those people, have you been getting past like TSA?
Just as you can. Okay, TSA is okay.
They don't care.
No.
When you go through the detective, it's DP, right?
Yeah, they pat me down every time,
Oh, okay.
but they say, what is that? And I say, okay, I don't know.
Okay. Cool. But yeah, that's a beautiful thing. Thank you. Yeah, I guess the only thing I want to mention about electromagnetic side signals is some terminology we use. First of all, how are we going to pick up this data? You can't just see electromagnetic radiation, unless of course you can plant magnets in your hand. So instead we use this device called an oscilloscope. It's super cool. If you have one, you should definitely use it. But basically, it's going to measure the whatever you're interested in, the voltage, electromagnetic stuff, whatever. And each time we take a sample, that sample we call a trace. And so here we see an example of a trace. It's just basically peaks on the graph. And the peaks tell us, hey, something happened here. But yeah, this terminology is going to be useful when we start talking about voltage or rather power. So in a computer, ideally, everything is constant time. But as we've seen before, not everything is handled the same. And it's also true for power consumption. In any CMOS devices, CMOS just means something oxide superconductor. No, what is it? Oh, okay. It's it's basically battery. It's just a fancy way of saying this is a certain type of device, but happens to be most of the devices that we use. Critical metal oxide something. But anyways, in these devices, it has been shown that different operations consume different power. This is true on multiple levels. For example, some operations are going to consume more power than others. Multiplication is inherently more difficult than addition, as we learned in elementary school. Additionally, big numbers are harder to deal with than small numbers. So we can kind of figure out what data we're working with. So for a power side channel, the idea is we're going to use our oscilloscope to take traces of the power output. This would be like the power of the device specifically that's running the process. See how much power it's consuming. In what context would you use this? Well, let's say you bought some proprietary software that does some encryption stuff, and you're like, hey, I want to figure out what secrets they're using. You can just measure the power supply of your device or how much power it's consuming, and you can pick up these traces. In reality, there's a few different ways we can conduct a power side channel. The first is just a simple power analysis. We just look at it, we take the trace and we see, oh, hey, stuff happening. As you can see here, we see that some peaks are big and others are not. This is because bits are handled differently. I think this is specifically, yeah, this looks like RSA to me. This is going to be an example about square and multiply. So every time we have a 0, all we do is we just square. We see it's like that. But every time we have a 1, we square and multiply. That's why you see a small peak and then a big peak. And so just by looking at the power output, we can say, oh, this is legit just the key that they used. You can just look at it and figure it out. Very simple, right? That's why it's called simple. Most of the time, life isn't simple. Instead, we need to use differential power analysis. Basically, the environment is noisy, doing stuff, capturing traces is difficult. There's going to be noise. As you can see in that picture below, it's very jagged. We can't make out the nice lines. So the idea for this is statistics is cool. If we take a ton of samples, we can use the power of statistics to eliminate any noise. Because even though noise affects our results, it's random. So over many, many samples, we can eliminate that effect. And so you can really just see here, we took a bunch of samples and then we essentially averaged them out to get the average, and then we take the difference, which is why it's called differential power analysis. And you can see at the very bottom, now we have those specific peaks that correspond to our zeros and ones. And then another idea is correlation. Basically, if we've been doing this for a long time, we kind of pick up patterns. Hey, when we work with this data, this is what the power trace sort of looks like. And so then we can just correlate how related the data we received is to known data samples. So that's all of the how and why of power side channels. Any questions? Idea is pretty simple. We just take a power trace, measure the consumption. The really cool stuff happens when we take it one step further. This is known as supply voltage coupling. Basically, we have our device. It's part of a circuit, right? But there's other things attached to that circuit using the same power supply. If our current power output in one device is going to change, it's also going to affect other devices in our circuit. So for example, we can imagine, hey, this right here, that resistor you see, that's our device running the critical operation we want to uncover. Meanwhile, we have an LED connected to it that's also going to be affected. So the idea for this is, one example, think about nowadays how we just use our cards to boot everything. You know, you want them to get into a place, we have electric lock. You just boot, and then the light flashes, and then you're in. Or if you're paying with your credit card, you just boot, and then there's a light on that thing, and it does the payment, right? Yeah, James.
I don't know if I'm gonna steal your thunder here, but our at UF, our ID scanners, you can't actually read someone's ID from the light on. There was research on it.
Wait, there's research they couldn't do?
You can, like you could.
Yeah, yes, they can. Yeah, exactly. Yeah, I know, that's really cool. Yeah, I was actually talking to one of the people that published that paper, and he's the one who introduced me to side channels, actually. So this is really cool that you bring it up. But yeah, all of the things you see at UF, those are vulnerable to side channels. Yes.
So with power side channels, is there software on your computer that actually records this voltage, or would you have to actually have physical control of whatever you're trying to crack?
Yeah, so there's two ways you can go about this. One is a software-based approach. There are commands in Linux that can measure the power supply. So you could just run that and detect. But obviously that requires you to be able to run software on that device, which most people aren't going to allow, because then you can just do a power tag. In that case, you have to use your oscilloscope to like poke at it and pick up the power output. Good? Cool. Any other questions? Okay, cool. So yeah, basically all of the scanners that you have, if you look at the light and take a very detailed picture, you can figure out what's going on and pick up whatever secret key was used to do this stuff. Another example that was proposed recently is, imagine we have a secret room, like this room, where we're having some kind of high confidentiality discussion going on. If there's like an Alexa device or like a Google Home, something that picks up audio output and is connected to a power supply, it's going to behave differently depending on what's said, right? That is connected to a power grid network that we can connect our own devices to. It doesn't have to be immediately next to the room. It just has to be the same power grid, not power grid, but same power supply as the whole building. Okay, so we can just go to an outlet nearby, outside of the room, plug our device in there, and just record the changes in the power supply. Yes.
Or an extremely old school side channel attack. Well, I say old school, it's not that old. During the Cold War,
Ooh,
the US, I think it was the NSA, I can't remember.
okay.
Or they even this, I don't know if it was the CIA. Whenever Soviet diplomats would come onto US soil, in rooms that only the Soviet diplomats would be in, that they were discussing, they would shine a laser, high precision laser at the window and record the vibrations off the window.
Oh, that's so cool. Yeah, that's wonderful example of a side channel.
Wait, what were they recording?
The vibrations in the window,
To find out what?
they were saying.
Oh.
It's as you talk that creates, pressure waves that's going to vibrate the windows. There's actually modern examples of that too, using the vibrations to detect what's being done. Yeah, cool. Any questions? No? Okay. How long have I been yapping? Oh, it's 1 hour. Okay. Do you guys want to call it a day there? Or do you guys want to explore more side channels? Yeah, you like that. Okay.
Midterms.
Yeah. I think I'm just gonna end it there. I've had fun yapping. If you're interested, feel free to talk to me about it. But I do want to say a lot of where I got this information was this. This guy, Daniel Russ, I love him. He's the best researcher I've ever seen. He does mainly side channel work. And the really cool thing is every time he discovers something new, he hypes it up so much. You can see he's gonna design logos for his attacks he discovers, like his Spectre and Meltdown, two super famous attack vectors. He just makes a cute logo, makes a website, publicizes it. Also, sometimes he makes music videos for his research papers. You can see here, which one? Yeah, the YouTube videos here. So this one here is a parody of Poker Face, and it's about college races. And then this one here is actually a full-blown sitcom teaching people how side panels work. It's 30 episodes, and unironically, the best show I watched. So if you're interested in side channels, there's a lot more information, a lot more cool things to talk about. Thank you guys for listening. Bye.
You have to go third.